This is a lesson on the mathematics of the superposition of 2D waves, also known as interference of waves, in the Introduction to Waves unit. And this is a calculus-based engineering physics course. So we're looking at some advanced, somewhat advanced techniques, mathematical techniques for adding waves. Just a reminder about 2D waves. We have our 2D wave equation. It is a multivariate wave equation where it has a dependence upon position and time. So we have some displacement of a particle on a 2D wave. This is a mechanical wave, so we're looking maybe at a wave on a string, or sound waves follow this as well, where y is the displacement of the particle. We can look at the angular frequency, or the number of cycles per second, omega. There's a wave number k, 2 pi divided by lambda, which to me represents the number of cycles per meter. We have time and position, and then also this phase angle. This is dependent upon whether, where we start time equal to 0. And I will say this is written as a sine. You could also represent it as a cosine. So interference requires us to add multiple waves at once. We're going to do the simplest case of just adding 2 waves. So when we look at the wave equations for 2 waves, we can see that they have their own amplitudes, their own omegas, their own k's, and their own phase angle. However, this is an introduction to physics class. There are some simplifications that we're going to make at this point in order for you to acclimate to the techniques that we're using. So some key assumptions and requirements that we're going to use for the intents and purposes of sound waves or waves on a string as we're heading towards standing waves and resonance is these waves will have the same amplitude. They'll have the same speed and omega and wavelength. Okay, so that makes instead of A1 and A2, we're just going to have an A value. Instead of omega 1 and omega 2, we're going to have an omega value. Instead of a K1 and a K2, we're going to have just a K value. There may be some independent phase angle. These 2 waves, even though they have the same physical qualities in terms of amplitude and speed and wavelength, they may not peak and trough at the same time, right? Which is what would be representing the phase difference. And it may be some absolute phase difference or some relative phase difference between the 2 waves. Okay. If we are looking at beat frequency requires that there's 2 different omegas, 2 different frequencies, and the techniques for adding is going to be similar. We will use a trig identity. Good old sine plus sine. You could use a cosine plus a cosine. That isn't too hard either. You get 2 cosine terms if you're adding 2 cosines. We're looking at sine functions here. So the standard convention in physics text, you'll see it. This is sine plus sine. If you are given a cosine function, you can always convert it to a sine function by just adding 90 degrees to it. Okay, so that's something that is achievable, not a major obstacle. So I picked out a problem. This is the problem superposition of speaker signals. A microphone situated at the origin receives signals from 2 speakers. One is located on the x-axis at x equals 2.5 meters, and the other is on the y-axis at y equals 2.1 meters. Both speakers are adjusted so that each speaker perceived by the microphone is they have the same amplitude. So that follows our assumption that I talked about in the previous slide. The speakers are in phase with each other. That is, they deliver a signal with no phase shift between them. So when they leave the speakers, there's no phase shift between them. When they reach the microphone, however, they may not be peaking and troughing at the same time. So this is a coordinate system for my speakers. Notice this is a different x and y than for the x and y in our wave equations. I'll get those going in a second. So I'm going to call this speaker 1 on the x-axis. We're going to notice that it's at 2.5 meters away from the origin. Speaker 2 I'm going to put over here, speaker 2, and this is 2.1 meters here. The microphone is right here at the origin. We'll call that microphone. Okay. So if I were to start writing out wave equations, I can have a y1 and y2. So this is for the mechanical particles of those sound waves. So y1 of x and t and y2 of x and t, they're going to have the same amplitude. That's what the problem says. And then continuing down here into the second paragraph, it says the rest of the equation, we're not going to consider the kx term. We're just going to go with the omega t term. So we're going to have a cosine omega t minus phi 1 and a cosine omega t minus phi 2. And you may be asking if they are originally in phase with each other, right? It says when they're delivered, they deliver a sound with no phase shift. So you might be thinking that these phi 1s and phi 2s might be 0 because they're in phase with each other. That's true when they leave the speaker. When they arrive at that microphone, they are not in phase with each other anymore. Okay? So I think the easiest way to do this problem is not to have a phi 1 and phi 2 as the problem suggests, but to let the one wave be out of phase from the other. And so this is what I'm going to call a relative phase shift. I'm going to call phi 1, 2 equal phi 1 minus phi 2, whatever that value is. I'm going to assume it's positive on some level. I'm not exactly sure. So what I'm going to do is I'm going to get rid of this. I'm just going to let speaker 1 arrive at the microphone with this equation, and then speaker 2 is going to arrive at the microphone with some phase shift relative to the first wave. I think that's the easiest way to think about this problem, is when they reach the microphone, you know, whatever's going on here, this one might be, you know, wherever it is in it, and then this one is at some other point in its motion, right? They're not peaking at the same time. They're not the same point in their cycle. And so we're just going to represent that with a phi 1, 2 relative to each other, okay? How would I find that value? That's a good question. I don't know if you were thinking that in your mind, but that's what I was thinking, is how might I find that? Well, I can look at the phase difference between them. They travel a different distance. I can see one travels 2.5 meters and the other travels 2.1 meter. So I might say that the difference, that angle here, is related to the path length difference, which we know how to find path length difference, right? L1 minus L2. L1 minus L2. And then if I divide by lambda, that's some fraction of the cycle, some fraction of the wavelength. And then if I multiply by 2 pi, that will give me radians. I'm not sure if that's all tracking for you, but that's how I'm going to do that. 2.5 minus 2.1 divided by the wavelength 1.1 and multiply by 2 pi. All right, so that's my phase angle between the two waves. So that kind of allows me to set up these equations, because you know what our next step is going to be is to add these two. Okay. On the previous slide, I had the sine plus sine alpha plus sine beta, and there's an equation there. I'm going to remind you also about adding cosines. Cos alpha plus cos beta equals 2 cos alpha plus beta over 2 times cos alpha minus beta over 2. So you can see the only difference here is there's a cos, and a cos here. If this was a sine, it'd be sine, 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 and then the cos term on the end stays the same. Okay, so I think I can move forward with adding these two waves. I know my alpha, I know my beta, and so I can add these two waves, right? I can say that this term is alpha, and then this whole term here is beta, okay? And then when I plug this into my trig identity, I'm going to get 2, and I'm going to remind you there's an A out front on both of these, so I can put a 2A. 2A cosine omega t plus omega t minus phi 1, 2 over 2. Cosine omega t minus omega t plus phi 1, 2. I distributed that negative over 2. Okay. Let's simplify a little bit. We have a factor of 2 omega t here and a factor of 2 down there. So the 2's will cancel. I'm going to keep that for a second. These two omegas cancel with each other. And when I look at this term overall, this becomes a constant value that doesn't depend on time. Okay. So when I look at adding my y1 of x and t plus y2 of x and t, I'm going to get 2 times the amplitude. They tell me the amplitude down here is 2.7. 2 times 2.7. And I'm going to keep the whole, all of the constants together. So I'll get cosine of phi 1, 2 divided by 2. All right, so this is the amplitude. This is the resultant amplitude, which I'm going to call A12. And then I'm going to have this time dependent, right, cosine omega t minus phi 1, 2 over 2. This is the time dependent. All right, this is our time dependent, where it comes time dependent. Okay, so as time changes, how I get the different values on here. I'm not at the peak, I'm not at the trough, I'm somewhere in between. So time dependent will tell me that value. But if I'm looking at the amplitude of the resultant wave, this would be A12. Okay. And so that's what the problem asks you to find. What is the amplitude, the resultant amplitude? So I would take 2 times 2.7. I don't know where that point went. Cosine of my angle divided by 2. So cosine of 2.5 minus 2.1 divided by 1.1 times 2 pi divided by 2. You can see that those cancel there. And so A12, that's the amplitude, the resultant amplitude of the two waves. When you multiply all this stuff together and make sure that your calculator is in radians, not degrees, you're going to get 2.24325. And there's a meter on the end because this is a physical dimension, an amplitude. Okay. I will say that if you wanted to find phi 1 and find phi 2, you could possibly do that. I would say you can find, what proportion of a wavelength those speakers have traveled. So like 2.5 over 1.1. Speaker 1 travels 2.5 meters, and the wavelength is 1.1. And then if I multiply by 2 pi, I can say that's the phase. That's the phase angle there. I could do the same thing with the other one, 2 pi. Notice that when I subtract them, I get the same equation that I had come up with before, L1 minus L2, right? If I subtract those two. You could use that equation if you wanted to. You could use those up in here and keep your original plus phi 1, 2 plus phi, and just keep this phi 2. And then you'll find out if you move through the math, you're going to end up with the same term down here. And I think for me, it's elegant to just realize that I don't care about their absolute shift. When I'm adding two waves, I care more about their relative shift. Where are they in phase with each other? Not where are they in phase with some random point in space, but where are they in phase with each other when I add them? And you can see that was the major term in this problem. I picked out another problem here. This doesn't fall with the assumptions that we were looking at with same amplitude. I can see that there's some sort of same frequency with this one. But what I wanted to show you was the geometric or phasor method of adding waves. I think it's maybe good to lay the foundation here for adding waves using a geometric or phasor method of adding waves here. As you move towards circuits and maybe RLC circuits where you have a phasor diagram, understanding how to use vectors to represent waves or wave motion or even with circuits, a current. You can use a vector diagram to represent current. So this should feel pretty familiar for you. What we're going to do is just let this represent a vector in space. Let me do something real quick here. Instead of having a cosine and a sine, I'm going to switch this up so that I have two sines. So I'm going to say this is 203 sine omega t plus pi over 2. You're okay if I say that? Cosine is sine plus pi over 2. So I'm just going to add that pi over 2 in there, plus 396 sine omega t. Okay, so what I'm going to do is have these represent two different vectors in space. All right, and you'll see where this is going super quick, super easy. If I let this one be wave 1 and then this one be wave 2, all right, let this be y2 and this is y1. I can represent the first wave like this. I'm going to let this angle here represent omega t, all right? And so this is 396 some angle. And then what I'm going to do is add another vector on. I'm going to add 203. So if I let this be the original one, this guy's going to get added at 90 degrees from here, right? This is a 90-degree angle. So if this is omega t, I'm going to go omega t plus 90. So that's this thing here. So this is 203. All right, and this is 396. There is a right angle here, and that has to do with the trig substitution I did. You could do this for some random angle, and let me put some random angle in here. All right, so if that's omega t, if there's some, what I'm going to call some delta in here. So this 203 could be at some random angle. It'll be sine omega. It'll be omega t, this omega t, plus the delta out in space somewhere, all right? And what we're going to do is we're just going to add these two like vectors and find the resultant vector, okay? So that's why we're using geometry. Notice that this is not an analytical, like algebraic method, but it's more geometric. For our specific problem here, we're going to have like I had drawn before, the 396 here, and then my delta is 90 degrees, so that I just have a super simple right triangle here. Okay, so I think when you look at this problem and it says, you know, express this function as a single sine wave, and you're thinking analytically, how do I add cosine and sine, and there's two different amplitudes, blah, blah, blah. This is why we use the geometric or Phasor method to make it easy to do this problem, okay? I'm going to remind you in geometry, let's see, we have the law of cosines, right? If I call this amplitude 1 and this amplitude 2 and this amplitude A1, 2, for my general form, for my specific example here, it's going to be easier. I could just use law of cosines in order to add these up, right? A1 2 squared equals A1 squared plus A2 squared plus 2A1 A2 cosine, and it turns out you can use that delta in there because cosine of that angle is the same as the cosine of 180 minus delta, which is the one that we really want. But because of that identity, we can just put delta in there. Okay. So for this problem here, if I want the A12, or what they're calling just A here, I'll just call it A. This is just the A value. I'm going to have A1 squared plus A2 squared plus 2A1, A2 cosine pi over 2. We like seeing cosine pi over 2 there. If you're a big fan or have the unit circle memorized, you know that's a zero term. And this is falling into what we already know about our specific example. We have a right triangle. So I'm just going to use right triangle trig on here, right triangle Pythagoras, right? We're going to have 396 squared plus 203 squared square root, and that gives you a value when you run that through your calculator of 445. I'm not sure what the units are on this here. I'll put units question mark. We're not given units, but if there were units, you'd want to include it in there. Okay. So that's law of cosines. If I wanted to find an angle, let's say, what is the angle of the resultant vector here? I will call that, I'm picking a different color for us. I suppose that might be this angle here. Okay, that's what they're calling phi. Is it what they're calling phi? Nope. Nope. It's going to be this angle here. It's from omega t, right? When I look at this, I'm going to be adding an angle omega t plus phi. So I already have omega t here, and then I'm going to add the phi here. And so that would correspond to r phi here. If I use law of sines, that wouldn't be too hard to do for this problem, right? Sine phi over, let's see, A2 has to equal sine delta over A12, right? If I look at those two sides, this angle, that side and that angle, and then phi and the other side. So I can find sine phi equals A2 sine delta over A12. For our problem, this becomes pretty easy. I'm going to get 203 sine pi over 2, which is 1, divided by my resultant vector, 445. And when you run this through your calculator, you're going to get 0.474 radians. That's it. Okay. Again, I think this might look like an intimidating problem. And I did want to take a moment to show you how to use the geometric or phasor method of adding waves so that you can see the elegance that comes from this method. Instead of doing all the analytical stuff that we did on the previous page with the trig identity, we can just use what we learned a long time ago with law of sines and law of cosines in order to find the sides of our triangle and the angles in our triangle here. So pretty cute method. So feel free to try that on any of the problems that you come across.